All right, let's quickly finish up this idea of transverse and longitudinal waves. We're going to talk about longitudinal waves now, ideal ones. And if it's longitudinal, the key idea, as we talked about before, is they are parallel to the wave motion, the vibration is. So again, source of every wave is a vibration. So let's introduce the vibration here. So here is your source vibration, creating the energy, doing work on that medium. And when it goes back and forth, what it actually does, it creates compressions, because longitudinal waves are also called compression waves. So you'll notice that we have some compressions here. We'll just label them. Let's label the first compression as C and the next compression as C. We call these successive compression regions. And in between, so the C represents compression. I'll just put that at the bottom here. So C represents compression. In between, we have what's called R. And R represents rarefaction. And so compression is basically high density. And rarefaction is low density. Good. So far. And what you have to realize is the particles here are actually still moving parallel to the motion. So every particle here, you just choose any particular particle here, they're moving back and forth like this. That's the particle motion. And the wave here is going to the right. So you can see those are parallel to each other, therefore a longitudinal wave. The only other thing we should know about this wave is how to determine the wavelength. So if you want to find the length of one cycle, here's what we recommend. You go from the center of one compression to the center of the next compression. And that length we'll call the wavelength. That's the easiest way to measure the wavelength for a compression wave or a longitudinal wave. Okay, so that's a longitudinal wave. You understand that in this course, the transverse waves are much more important. So to finish this up, I have a little activity here for you as a note. Let's talk about what happens when there is friction. Because friction will cause the wave to lose energy. And we want to see what that looks like for transverse and longitudinal waves. So let's start with transverse. I'm going to get you guys to just think about this one. Just pause. Think about what you think it would look like if in fact there was friction present. All right, so for the first one, again, we're going to assume that the source is on the left-hand side. So here's where the source vibration happens to be on the left-hand side, creating the wave, and the wave is moving towards the right, as a transverse wave would do. Now, underneath it, I'm going to put our new one where friction is present. So the first one is considered ideal. The second one will be what happens if there's friction. And the idea is that because there's a loss in energy, the energy of a transverse wave is the amplitude. So it's going to start with a really high amplitude, as we see in the diagram, but then the amplitude is going to get smaller and smaller and smaller and smaller. So it kind of looks like this. Testing my drawing skills. So the wavelength, notice, is staying the same, but it's decreasing amplitude. So the amplitude decreases. If that's what you were thinking, good for you. This is the effect of friction, is it'll reduce until it has no amplitude anymore and it's disappeared. Good? Okay, so that's our first one. Now let's take on longitudinal. So longitudinal, now we have a vibration going horizontally, and the wave is also moving horizontally, parallel to each other, longitudinal wave. And this one here I kind of drew as a spring, but I have a tough time doing that. So I'm going to show you another technique. I'm going to show you as like a density column. And I'll get the point across though. So you can see over here, the first one is an ideal wave. But the next one is, well, what actually, at the beginning here, here's another way of representing high density. It's lots of dots. very close together. So that's the compression region. And then in between, you have the rarefaction area. Okay, so that's another way of actually showing high density. And it turns out that when it starts losing energy, and I'll just kind of give it away, here, the density kind of represents the energy, and the density will start to decrease in the compression. So if we get to the next compression, so I'm just going to put maybe not the same color. Okay, let's use a different color so I can highlight it for you. We just want to make sure it's clear to see. So here's our first compression region. Here comes the next compression region. Well, I guess I can't even do that. Ah, darn it. That seemed like a good idea at the time. Anyways, let's just draw it the best way we can. So the next one will have less density. It's still going to be more dense. It's probably a bit more spread out as well. You see how it's still more dense than the rarefaction region, because there's your compression, here's your rarefaction, here's your next compression, but it's not as dense as the first one. Then it's much less dense. And then the next one, it'll be a bit more dense, but less dense than the previous one. So the density decreases. Good enough. That's about as best I can draw for this one. That's a hard one to draw. Okay, so now we get a feel for transverse waves and longitudinal waves. We're now ready to take on the mathematical side, and that'll be our next lesson. I'll see you there.